Okay, my outstanding friends, this is one of the biggest discoveries in mud fossil history, and I'm not kidding you. We're going to be discussing banded iron formations. Now, I'm going to jump right into it because I have them here, and I'm going to show you what they show, what I show, and what I believe, and what they believe, and you can take it from there. Okay, I am here to admit that I think I was wrong about these little stripes in banded iron being strictly due to fibers separating like membrane layers. Now, there is a ton of that in the body, absolutely no question. So I saw this and assumed that. However, looking at the way blood separates between the red and the black, it's not just that there's fibers here separating the black and the red. That's polarity. It's polarity. That falls right into dipole electron flood theory, because those two types of iron will oppose each other, so they separate. So they create these separation patterns. They don't have to necessarily be strictly from layers of tissue, and I know I can prove that because of my banded layered iron, and it's not in actual perfect layering, and that's because this is within an organ. Now, that could strictly be organic layering. However, it's still going to have that push to shove. So you're going to have the red up there and the black down there, and then the red below that, and then the red black below that, and then just exactly what you see. It's one after the other. It's not two in a row. Some of them are wider, some of them are narrower, but that's just the way it works. It's going to push to shove, to push to shove, to push to shove. Case closed.
Jobs like welding or mechanics, just some of the many practical skills students are learning in more than 70 agri-science courses offered at Glastonbury High. And the program's not only for the boys.
I grew up on a farm, so I grew up with my dad and my brother who work on a lot of engines.
That's Natalie Horton, a high school junior. She's taking this equipment systems repair course to build her vocational knowledge, to land future jobs and fix future problems.
For instance, like the car you drive, like some girls probably don't even know like how to change their oil or like their tire, and like if they're driving alone on the highway, they'll have to call somebody else to come out.
And educators say with the cost of college on the rise and the need for more skilled labor, exposure to agri-science might be the perfect match for those getting ready to enter the workforce.
We need people who know how to do things, right? We're at a point in society where the doers are aging out, and this hopefully will help create a new generation of doers, people who know how to do things and aren't scared to try.
In a place where doing and learning collide.
Hands-on learning is where a lot of people shine.
If you are a Connecticut student interested in this free program, Glastonbury High is currently recruiting for its fall 2025 class. You don't need to be a student in the district to qualify. For a link how to apply, it's on our website, fox61.com. In studio, I'm Bridget Piorlo, Fox 61, Connecticut's news station.
Courses that are being taught in Glastonbury. If you're not familiar, it's sort of an extension of what we used to call STEM. It now stands for Science, Technology, Engineering, Arts, and Mathematics. One of the other courses is Applied Robotics in Engineering, where, of course, students do a lot of hands-on learning. And speaking of hands-on, look at this. In this class, students actually navigate a prosthetic hand with a remote control and use it to communicate in sign language. The students say it's a useful exercise in both problem-solving and critical thinking, and that's to say nothing of just the inherent cool factor of doing it all in the first place, right?
Okay, my outstanding. Okay, my intellectually superior friends, prepare yourself for banded iron. What's banded iron? Well, according to this guy, he says the rocks we're standing on are something called, in general, banded iron formations. Let's look into that, because iron is what your blood is made of. Blood in your iron in the blood is just there's tons of it, and it carries the oxygen around in your blood. Now, why is there banded? What's the banding about? How do they explain that? And how do they explain the iron just congealing into this banded formation? I do the mud fossils, and I'm going to show you what I think compared to what they think. So it's just, you make your own determination who's thinking the right way or the wrong way, or maybe we're both thinking the right way, maybe both thinking the wrong way. This is up to you to make that determination, but in order to make that determination, you have to take a look at the evidence, and here it comes. Okay, so what are they saying about banded iron? Now, this is saying from a geological standpoint, this place they're at right now, Jasper Knob, is arguably the most famous geological, let's let this play for a second.
From a geological standpoint, Jasper Knob is arguably the most famous geological locality in the Lake Superior region, and I would be one of the ones that argue that it is. I've been here, I'm sure, at least 100 times personally, and I've brought hundreds of people here, from a small group to busloads. I've probably brought somewhere between 500 and 1,000 people here just to see this.
So you're part of the reason it's so famous.
Well,
you keep dragging people here.
Many other people come here for over a very long period of time. So the rocks we're standing on are something called in general a banded iron formation, which is a very descriptive term. It means it's an iron-rich rock and it's banded, which we can see in a number of places as we walk around the outcrop here. And generally the banding is a layer of silica, commonly called chert. If it's red, it's called jasper. Then the intervening bands are some particular iron mineral. Here, that iron mineral is hematite, which is a nice shiny silvery, so it makes it especially spectacular here.
Yeah, wow. At this point, I will briefly note that Jasper Knob is an example of a superior type banded iron formation. There are a couple of other types that formed in different environments.
Okay, she's talking about the general geology explanation, and this guy's brought thousands of people out there to tell them what they should think about this formation, and I don't think he's got it right. Let me show you the formation they're talking about. Okay, my friends, hold on to your hats. This is Alexis Dahl, and she's talking about modern life depends on this extinct rock, banded iron formations. What does she mean, extinct rock? She doesn't mean it in the sense of mud fossils. However, I will explain exactly what she's talking about. She's talking about banded iron formations. Now listen to what she says here. Hold on. Let me crank up the volume a smidge. Listen to this now. So this is Alex Dahl channel, and modern life depends on this particular rock. Let's see what she's talking about. Here she goes.
Hey there! This rock is the backbone of the global iron industry. It's called banded iron.
All right, it's called banded iron formations. What is that? And do I know what it is? Yeah, I do know what it is. And do I have any of it? Yes, I do. My motto is, if I ain't got it, there ain't any of it. So hold on, I'm going to show you exactly what this is. And she's talking about it being an extinct rock formation. Now I'm going to explain what she means by extinct, and I will explain what I mean by extinct. I think they're not going to be the same. Okay, this is going to be fun. This is her explanation of extinct, why the iron formations are extinct. Here she goes.
The global iron industry. It's called banded iron.
Wait a second. Okay, so that sets you up. What she's going to be talking about is why this rock is extinct. Why would she say the rock is extinct? And here's her explanation.
Hey there! This rock is the backbone of the global iron industry. It's called Banded Iron Formation, and it's responsible for most of the iron we're mining today. But here's what I think is more interesting. This rock is extinct. Many of the rocks you can find around you today are still forming somewhere on Earth. Lava is cooling into basalt, sand is slowly being compressed into sandstone, but with the way our planet is now, banded iron formation can't form anymore. In that way, it's extinct. And
well, that's her, you know, it can't form anymore. Well, what did it form from? What did banded iron form from? I think I can explain it, and I have some here that I can show you. Okay, so she's saying it's extinct. Let's let her continue here.
And honestly, I'm glad. It's story time. I have wanted to make this video since, very specifically, the day before I moved to Michigan's Upper Peninsula, which was in December 2020, almost 4 years ago. But there's a reason it's taken me this long. Here's what happened. In 2020, I was living in Ann Arbor and was just getting interested in geology. And I came across this article talking about a boulder on the University of Michigan campus that I know I walked by dozens of times as a student without ever paying attention to it. Like, for an entire summer, I rode my bike to work straight past this thing without ever knowing it was there. So the day before we moved, I headed down to campus and was just charmed by this thing. I mean, it was a little covered in bird poop, and hey, I wasn't at my best in 2020 either, but check out these layers. I had so many questions about how something like this formed.
I have the answers. Alexa, this is amazing. You have the questions? Alexis, I have the answers. This is great. I'm going to contact you and see if you're interested really in the answers. I have them right in this rock right here, which is banded iron. Okay, before I show you my iron formations, I am going to let her explain about what they say at this university where this rock is.
Just look at it, and I never look down. I always want to tell them, look at that stuff you're standing in.
If you've watched the series for a bit, you have probably seen Dr. Cannon. He's a scientist emeritus with the U.S. Geological Survey and has been studying the geology of Michigan's Upper Peninsula on and off since the 1960s. I have now lost track of the number of times I have looked up a paper about Michigan's geology and found him listed as one of the authors. So I asked Dr. Cannon if he'd be willing to read my outline and suggest any corrections. And after reviewing it, his response was essentially, "We should talk on the phone." Here was my problem. Early on in my research, I had come across a couple of sources that are usually very credible that gave very similar explanations for how banded iron formations formed. And it went something like this. Once upon a time, about 2.5 billion years ago, Earth's atmosphere had much less oxygen than it does today. During that time, there was a lot of dissolved iron in the oceans.
All right. I'm not going to drag you through this because this goes on for a while. It's the typical thing. It's just settled here and then it's settled there, and Fe2 was a little heavier than the Fe3 or vice versa, and it just causes these formations. Well, where did the iron come from in the first place? And why was it all over the entire world in these oceans? And why did it only form in little pockets here and there? It's not everywhere on the whole world. And it's not like in gigantic oceans either. Well, some is, because the things I'm going to show you are gigantic. Now, I have a whole different idea. So if you want to watch this whole thing, you can. But this guy here is talking about how
I'm
this.
a football obsessed man.
When all
You see this? This just proves my theory about Lake Superior. It says the whole Lake Superior region was mantled by a single layer of banded iron formation. The whole Lake Superior region. Mantled means covered by. a single layer of banded iron formation. Okay, I guess I'm going to have to start showing my examples because all it is biology. I'm sorry, Professor, you got it wrong, my friend. They're talking about magnetic rock. Well, it's because it's iron intruded into this after it formed. One sample of this rock was found at Tilden Mine, and the rock dated at 1.89 billion years old. They can't date these things. I'm going to tell you right now, they cannot date these things. Now let me show you what I have here, picked up off the surface of the Earth, and it is a banded iron formation. That is banded iron. Wait till I put some water on there, you're going to see. It's the same thing that they have, and it's in it's in layers. A little different than what they're showing, but it's still biology. They're showing this right here. All right. If you took this sideways, this is what they're seeing. If you looked up into each one of these slabs sideways, that's what you'd see. On the edge, it's too much, well, you know what? I'm going to put it in a microscope. We might be able to actually see this. Well, you know what? I can see a little bit of it right now. We might be able to see the sideways banding. I'll bet you we can when we put a little water on there. We'll actually see this banding here. You know, this is the banded iron. Now here's in my microscope, one that I have here is the same banded iron. Now it's from an organ though. What they showed in their shot is a fractured banded iron. See it down here? That's like, there would have been there would have been membranes here somewhere at some point, and that membrane's gone, and it's fractured. So we're seeing sideways through the banding. Mine, we're looking down into one of these layers, which contains all of that stuff layered back and forth. So you got the red and you got the black. Now I got a little water on it right now, so it's a little bit moist. Let me dry this up before we take a look at it a little bit. Now, here it is in the microscope. And this is nothing but the same iron banding. Same thing. Now, I want you to see something very interesting. There's the black, there's the red, and again, we're looking down at the layering. So the layering is this way, but you see this? That's a membrane. This is an organ. The other one there is just like broken here, and you're looking in at all these layers. We can't really look in because it has a membrane. You see that different membrane? This is the black and the red of the black. Same thing here, black and red. Only we're looking down at a fracture of this size. Originally, it would have had a coating around this, which had a membrane on it. Everything has a membrane on it. This is not going to be, that's not standard. It had to be fractured away from a membrane. Now we still have the membrane on the one I have here in the microscope. Now I'm going to put a little water, just a smidge of water on there, and you'll see that membrane is a different situation than the rest of the stuff. Usually the water brings out the little fine details, but you see how black that is, see how red that is? That's a banded iron. Now this is the membrane. So let me wipe it up a little bit. And you can see, let me bring this down. Turn the light down a little bit lower. We might be able to see something from the side. I don't know. I have to really take a look. I'm going to do that in a second. But that's the banded iron. That's where there was a lot of blood right there. This is there's hematite and there's magnetite. The black is the magnetite, the magnetite. The red is the hematite. And there's all these little blood vessels, they're all mixed together in this banded iron because this is muscle, basically muscle. What you're looking at down here is muscle. All right. Now, what you're looking at up here is not really, I don't think, muscle. I think this is an organ. And when you get out to the edge, right here, I believe that's a membrane. Let me come right down on top of it. You see that white? At first I thought that was something I just rubbed off onto there, but I don't think it is. I think it's part of the tissue. We'll clean that up and we'll take another look. I got to come right down close. I'm scrubbing it good, so that white stuff is not coming off. That's part of it. That's not going to come off. All right, now let me come right down on top of that. All right, now, can we find that membrane? And I say, yes, we can. And that's it right there. Now let me turn the lights down. Sometimes you can see it better in a different lighting. But I'm going with the fact that that membrane coats. Here's a spot that might be better to see. I think that's a membrane that coats this whole thing. All right, so this itself was an organ, not muscle. This one down here, I believe is a heart muscle, and it's a heart muscle. And the reason, I know it just sounds crazy, but I believe it is a heart muscle, and it's just absolutely, well, he said that whole region is covered with this. And he's saying it's 1.85 billion years old. And, well, I totally disagree with that. Although I don't know. I can't disagree with that totally. I can say I doubt it. Now, let's look at the sideways of this in the microscope. All right, I'm going to run through this kind of dark so you can see the colors. We're looking at the side of this thing. So it's cut like this. The banding would be banding this way, basically, and it's fractured. You see that fracture? You see these different colors? That's the colors of the black and the red blood. And here, this brownish looking color is a transitional area between the black and the red. You see, and it has these crack here, fracture there, fracture down here. Whoops. And it's all this red and black, and although I think this is an organ, I think this is the coating of the outside of an organ, and they have this little white strappy stuff on the outside of organs. It's called fascia. Now this one here is extremely eroded, so it's almost all the way down inside the organ. There's just a tiny little bit of that stuff left. You see this? This is the white stuff. That's the fabric that coats it. I could probably find a place where there's more fabric. But you can see that. See this stuff here? That's the coating of an organ. There's no question in my mind now that this was coated with this fabric. Hold on a second. Yep, no question. This is an organ. You see this? This is where the outer coating latches together. All of that stuff is the outer coating of the membrane. And it's just being, it's eroded down to a point where it's almost gone. There's tiny little bits of fabric here and there. And that fabric is from the fascia that coated this. The whole thing was coated with this kind of fascia and a wet, gooey stuff. I could probably find better. Well, actually, that's not bad right there. Let me put a little water on there. We'll come back to this in a second. Hold on. All right, this is probably about the best spot. Almost everything is eroded away, but you can see these little fibers. And it was a matrix of all these little tiny balls. You see these little black balls in there? And all of that was, I don't know if you can see that from that far away, but there's these little black balls in there. And there's a fabric here. That whole fabric, and I'll show you a lung, it's virtually perfect, that is completely surrounded with the fabric that I'm trying to show you. However, this one was extremely eroded. So if I get off of that spot, I get over to here, and we really have almost no fiber left. And I go a little further over, and it's more eroded. You see it? And I go over further more, and it's probably more eroded. It comes and goes here and there. But the main thing I want to show you is this. This is the part, which is the inside of this organ. You see that? That's banded iron. That's the black and the red, only we're looking straight down at it. You see all the little black balls? They're in the membranes. And every layer is coated with a membrane. Some of these are very, very red, and some of them are very, very black. That's the way blood works. When it's red, it means it has plenty of oxygen. When it's black, it means it's depleted oxygen. What happens is the oxygenated blood goes all through your system everywhere. And then it has to, once it's used, it's no good anymore. It has to go back through the black spots and get sucked back into the veins. And then it goes back through the vein system back up to the heart. And then that pumps it through the lungs and, through the liver and, cleans it all up. And that's exactly what we're looking at here. Is some kind of a organ, and I believe it's an organ. I don't think it's just, well, I know it's an organ because, I can't say that for sure. Because it also has fascia around it too. But this definitely has fascia around it. And it's got all these layers that they were talking about, and the spectacular silver look. Well, I don't know how spectacular it is, but there's your silver look right there. Hold on. I gotta focus. Slow down. Let me just lay that down. Hold on. You see that? That's the silvery stuff. If you watch that video, and that's coming out of some kind of a pore there. I don't know what it is. But you got this really silvery stuff, and then you got the real black stuff. And you got the real red stuff. And then you got all kinds of other stuff. Like I say, I think this is an organ. Having that fascia on the outside. Now look at this spot here. What's going on there? All I can tell you is that's biology. Let's get right down on that. Just see what we can see, if anything. Probably not. It's just going to be some kind of mineralization. And I got to turn the lights down. This is where you really got to play around and adjust everything just right. And don't forget, this is a different color than we're seeing in other places. All right, now let's turn the lights down low. You see the different contrasts of colors? Something's going on in here. I don't know what, but that's like a little bit different than you're going to see anywhere else. If you get it just in the right, and that's about the best I'm going to be able to do, to see the contrast of colors. But everywhere you see these little dots, that's where some kind of fluid was coming in and out of there. I don't know what. Maybe it's sweat fluid, or I don't know what it is. I'm not going to make any silly guesses. But it could be where there's lymph. I don't know. I just don't know. That's just the honest truth. But that, as far as I'm concerned, is the red blood of the banded iron, which it would turn into hematite. The magnetite is the black stuff. Now, this did not turn into like the heart muscle, which I believe this is a heart muscle. I believe that right there is heart muscle. That is my belief at this point. You see that? It's a separation of the little muscle fibers. You see how much blood there is there? Now, I watched their explanation of this, and you know, I don't have the same explanation, let's put it that way. Mine is it is biology. Okay, like I say, I have a total different interpretation of what we're looking at. But they're talking about banded iron formation, rough timeline. So think about this right now. What they're talking about is layer after layer after layer after layer. Now, this is what they're seeing, is layer after layer after layer. You see all these little cracks here? Those are just layers of tissue. And that's layers of tissue. So they're given the timeline, which is just like a zillion years ago, and coming up with this explanation of how this all formed. And
the new Bearskin Hoodie 4.0 claims to be the most advanced waterproof tactical hoodie ever made.
Well, let's see about that.
That two periods of folding that make this very complicated fold pattern that we see here.
And then one of the mysteries about this, I've heard this described as like an extinct rock, because it's not forming anymore. Is one of the mysteries why exactly it stopped forming, or do we have any ideas about that?
Well, you know, as I mentioned briefly before, one of the peculiar things about this banded iron formations on this scale is that they were quite common around the world up until about 1,850 million years ago.
They're quite common around the world. And then all of a sudden they stop. This is 1.8 billion years ago. How did they come up with this? All right, so here it is. They say 1.85 billion years ago, they stopped having this iron formation that ended at that time. And there's several explanations of why that happened. Well, let's hear their explanations.
That might happen. One is that there's something called the Great Oxidation Event, which kind of coincides with the evolution of photosynthetic microorganisms. They begin to oxygenate the atmosphere and the water. And to dissolve a lot of iron in water, it has to be relatively reduced. So if it becomes oxidized, you can't have large amounts of iron dissolved in the seawater. It's possible that the Earth just...
Well, where did all this stuff come from, first of all? Anyway.
Became too oxic. And myself and a colleague have proposed a while back, hasn't been very well accepted, that it may have something to do with the Sudbury meteor impact, which was a major impact event that truly modified things on a global basis. So perhaps something related to that is what made some fundamental...
All right, as you all know, I'm not going to bother going any further. He's right. Only it was Venus almost impacted Earth. It caused a global flood and killed all the giant creatures. And that is biology, my friends. There was just something going on here that was just overwhelmingly gigantic biology. And we're seeing this muscle on the surface sticking up out of the surface, and the flesh that surrounded it, the fascia, is eroded away. This didn't happen 1.85 billion years ago. You see all this stuff growing here? That would have covered it, but no. This stuff is right on the surface, and it's just washing away. It's not like something's piling on top of it. It's just right here, open to look at. But they just can't get their heads around it because it's so everything that we have thought is just wrong. Every single thing there is biological, 100%, and the sizes are astronomical. All right, that link was sent to me by Leon Welsh. And, you know, I've talked about these banded iron formations. It's things like this, which are stunningly, unbelievably red and lush with color because they're still biologically extremely active. And this is nothing more than a big wrinkled area in some body part, most likely a muscle. It's hard to say, but I can almost see the blocks of sarcomeres in here. But it's layered. And I believe that's the membrane in between the layering, and then this would have been the fluid-filled highway, which is now empty. And that's my take on this. Now, this didn't come from Leon, but I have people all over the world sending me stuff. And what do you make of this? This is right down the street from me. What's going on? That's my take. Okay. This is the banding, the black and the red. You see the red? I don't know if you can see that well. And then there's the black. The black is, I can see it very well. Now, this is laying flat, and the banding on this one, so we're like here, laying flat, and we're looking inside like we were looking down this and seeing the black and the red all mixed together, basically, is what you're seeing here. You see how the black changes to like silvery looking? It's drying out now. I had it kind of wet. But what you want to also look at is what's all this? What is this white looking stuff here? And again, this is the same banding that we would be looking at if we cracked that down the seam. And we would see the black and the red all mixed together, just exactly like this. This is an organ, though. I'm really almost 100% certain. And I got all kinds of layers that could come from this. And but what I didn't realize, I always thought this was only from muscle, and I don't think necessarily this is a muscle. It doesn't have the exact same characteristics as a muscle, and this does not either. This is absolutely not a muscle. So what is this, and why is it banded like that? I always thought it had to be the banded for the muscle, but it's not. I came to a new conclusion. Is because of the polarity of the black and the red. They push apart from each other. They separate. They don't want to touch each other. I always thought it was because one was the vein and one was the artery, and they were always sort of separated. But no. I think it's because when they get next to each other, they just sort of polarize away from each other because they're two different polarities, Fe2O2 and Fe2O3. And two different oxygen levels, and I think they sort of separate along those magnetic lines and push each other apart. Because I don't see the characteristics of muscle here at all. Well, I can't say that. I don't really know. I got to be honest with you. But I have come to that new conclusion that these things are separated along polar lines. All right, the black pushes the red away, and the red pushes the black away. It's dipole electron flood theory in rock. All right. You see the black and you see the red, and they're separated strictly, I believe now, due to pushing apart from polarity. Otherwise, they wouldn't settle in layer after layer after layer after layer just by themselves, unless they were layers of tissue. So we're left with those two possibilities. They're layers of tissue, or they push each other apart and cause these layers. Now, it's one or the other as far as I'm concerned. I see no other possibility. You know, the more I look at this, the more I think it is a polar separation. And I'm going to show you another place in the world that has absolutely enormous biology that they claim is geology, and it is separated from the black and white as well. I mean, the black and the red as well. And I always thought it was just because they bled from two different areas. But now I'm starting to think that they actually push each other apart. Because I don't see, you know, I don't know, this is going to take a little research, but I see them pushing each other apart from polar interactions, not necessarily from each of these little muscle bands. At first that's what I thought, but I have changed my mind. It's banded iron, but I believe it's polar banding. Okay, my friends, another shocker du jour. Angela, a good friend, sent me actually samples of these, what everybody was calling seashells, up on the top of her mountain. She's on the top of a mountain. And then he said, well, how do these seashells get up on the top of the mountain? I'm going to tell you right now, these are not seashells. These are lung alveoli. Now, if you're not familiar with what an alveoli is, inside of lungs, there's these little tiny holes, little bitty, 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 and the air goes in there, and right in here, it gets absorbed. And you can say, well, Roger, how can you prove that? Well, here's how I can prove it. She actually sent them to me. But I'm going to show you the pictures of what she sent. You can see the absorption actually happen, and it also proves my point that the oxidation states literally push the blood from the red to the black, or that type of thing. There's some polar push, as you'll see. All right, this is going to be fun. I got the microscope fired up and ready to roll. This is an alveoli. You see this yellow, you see the black, you see the red? Nobody's touching each other. Why? Why isn't that just sort of blended in? Those are absolutely, totally, get away from me. I'm yellow, you're black, you're red, stay away. Well, why? Why? Abrupt transitions. Now, she sent me a bunch of this stuff, but this, as far as I'm concerned, shows that there's some kind of polar separation between the blood, and this is blood. Those are the states of iron of blood, and this, as I will show you in a microscope, is part of one of these assemblies, and that is those are fibers, you know, the alveoli and the lung, and they're absorbing the oxygen and discharging the carbon dioxide and exhale. This is where the exchange happens, right there. So don't forget, these are the different transition colors of blood. Now we're going to be looking up in a microscope, and this is one of these little seashell looking things that they're talking about. All right, you see the black and the red? All right, there's virtually no, well, there is some yellow here and there, but not a whole lot. But you see these, they always thought these were seashells. They are not seashells, they are alveoli. And there's a zillion of them all stacked in lungs. All right, you see that? These are not seashells. Those are the colors of blood. Now, this is just out of control crazy, because this lung has to be just absolutely stunningly enormous for these to be alveoli, which they are. She was able to send the surface, which is where the membrane surrounds the lung. And then the alveoli start here, and then it would have been, I don't know how big it would have been, but it would have been enormous. And she was able to find that transition zone between the layer of the membrane that surrounds the lung into the alveoli. And like I say, this thing must have been absolutely enormous. Now, it is extremely weathered. That stuff there would have had like a pattern it would have been just like this. At one time when it was brand new, it would have been just like this. It would have had that fiber on there. Well, when they weather, that just went away. All of that stuff went away down to the basement layer underneath, which is this clay looking stuff. All right, but all of the fabric went away. But inside, just like inside of that, is going to be this stuff. Only in here, this thing here, I don't know how big it was, but it would have to be absolutely stunningly large. For this, right there, that little thing right there to be the alveoli, just think of the size of this thing. And there's one of them I found over here that's loose. I was going to take out. Maybe it already came out. Anyway, they're and that, I think, right there is where a main blood vessel was, because they're going to have big main blood vessels here and there, and then they branch off into these little tiny alveoli. And these little alveoli holes, they have like little tubes running right down the center of them. And in that tube, it makes that transition between the red and the black and the yellow, because that's the 3 different oxygenation states. And I'm not sure exactly what the yellow is, but the red and the black is Fe2O2 and Fe2O3. The 3 is the red. And they push each other apart because of that polarity between the 2 and the 3 state. You see this? This is absolutely phenomenal. She was able to catch this. This is basically the outside, where underneath here, whoops, is these what they call seashells. That's already flush with red blood. That's going to be transitioned into the body through these little tubes somehow. There's black, and there's red, and then there's yellow here too. The yellow is somewhere in the midst of the two, in between the two. But isn't that fabulous? I mean, I was shocked when she said, "I'll send them to you." I said, "Wow!" And thank you, Angela. She's down in West Virginia, and the discoverer of the mountain seashells. And something's going on here with biology. Look at this little thing. It looks like it's got 2 eyeballs. You know, you can see anything you want in stuff. I go for the chemistry. I go for the biology, the anatomy. It's stuff material science. That's what I do. But I'm no question whatsoever. The black is vein blood, and the red is the new, fresh blood, artery blood. And the yellow, I think, is somewhere in between. It could actually be lymph, but I don't think so. I think it's one of the oxygen states in between. All right, we're talking about layers and the transitions and the pushing and the shoving back and forth. And this is in my shop. This is a bone right here. Right there is a tendon. And going this way is the muscle. And it only goes a certain ways where it's mineralized, and then it just breaks right off here because it becomes just sarcomeres. Here it's pretty heavily mineralized from this abrupt transition where it's strictly a tendon here, 100% tendon. And then from here out, it's a little bit of both, a heavy-duty connective tissue with muscle, and then it just goes to straight muscle. And it just breaks off out here. But this shows it with the bone. You see all this red blood coming in there? Like I say, always pay attention to the little things that, they may not seem to make a whole lot of difference when you look at them quick, but this is the blood that is servicing muscle. Muscle requires a ton of blood. This is the tendon. Almost no blood at all. So we go from the bone to the tendon part, no blood, to the muscle part, a little bit of blood, a ton of blood. That's how muscles work, and tendons. Tendons have very, very little blood, but boy, are they tough. And the muscles have a lot of blood because they push in and out using that blood. Okay, what I just showed you was something I'm sure you didn't pay attention to, was this little ball. Of course, you only had a couple seconds to look at it. But right down the center here is the main support for a tendon. The bone was right up here. Why is the bone not there? Explain that to me, Roger. Well, I can explain it, and I will uno momento. What about, how did that stuff stop? How come you just sit here? What's going on? Here's my explanation. There was a bone right there, gone. There was a muscle started here, gone. Why? Why did they go and this not go? If this was, in fact, a big bone with a tendon with a muscle. Well, the key is this is almost indestructible. These things are just absolutely like unreal. And the center part is the main supporting part of the tendon. So here's what happens with the bone. And I'll show it to you on mine that I have here in the shop. It's the same thing, only I still have the bone and I still have the muscle. Right here is where it anchors towards the bone. Now, this has to do a little swivel here, a little swivel there. It's got to move a little bit, but it only goes like just about like this, almost no movement whatsoever, just enough to buffer it from being ripped out. It's a buffer zone. It's a tendon. It gives its tension. Now, so what happens? These have to slide among themselves, every one of these. But they still have to be tough as hell, and they are. This one is the toughest of the tough. And that circle right there, pay attention to the details. Remember, details, details, details. So why would I say details about this? Let me show you. You know, I got to go a little bit back to the drawing board. See this? I would have said that was a banded iron formation, and I think they would agree with that in geology. However, this is connective tissue. The white stuff is connective tissue. This is the bloody stuff that runs amongst the connective tissue in layers of muscle and tendon. And I can show you this in my own shop. I have exactly the same thing. And here it is right here. Hold on. All right, you see these layers? Those are the same layers that you just saw, and they're being fed with blood. When this was alive and in a certain condition, this would be just flush with blood. It would almost be completely blood. And I can show you them that are literally completely blood because so much blood accumulated there that the nucleophilic invasion was of blood. All right, so the blood substituted what was there. Not mud, not plant materials and all kinds of things and bodily tissues and residues. It depends on what the thing is entombed in as to how it preserved. All right, I think I've made this way clear. You got to understand nucleophilic invasion and substitution. It means that there's transition. Well, I'm going to show you. You're going to have to learn this. If you want to learn it, you learn it. If you don't want to learn it, go somewhere else. Let's step back because I'll show you transition in a minute. But you see these little breaks here? That's what is called, I call it abrupt transition. That's an abrupt transition. That's an abrupt transition. That's an abrupt transition. And then you get out into the muscle and it just falls apart. Now back here is this ball. You see this ball and this big heavy duty strap right here? That's the center of this tendon. And it can rock this way and that way because the muscle has to go this way. I think this might be a shoulder joint. And I'll show you why I say that in a second. And it has to have an abrupt transition that goes from the no blood, basically, no blood almost at all in the tendon. See how this is pink right away? And all the blood is running down here. That's all artery blood to service this, your shoulder muscle. And this, well, I'm guessing at that. But let me show you what it looks like in its entirety with the bone in, as we say. All right, so here's bone in. All right, here it is right here. Now remember I showed you that big round thing? That's it right there. All right, and somehow it attaches back to this, I believe. You see how this bone, and there's another circle here. These are some kind of on a little rotating deal going on. I don't know. somebody with an engineering background might be able to look and say, oh yes, if this thing turned that way, this thing would turn this way, or that would turn that way, or whatever. But it looks like it's got some kind of a strap that anchors back here at the back of the shoulder or the bone or whatever it is. Now, this, I would say, is the outside skin. Basically, that's the skin. And right below it is all of the, you know, let's say it's right here on your shoulder. That's what I'm thinking, but I could be totally wrong. But let's say that's right up on your shoulder. And there's basically your shoulder bone area. And then it comes down with a heavy-duty tendon right at the edge of your shoulder. This would be the outside of your shoulder. And then right into your muscle. Maybe. That's the biggest guess in the world. I have no clue, to be honest with you. But I can tell you what, this is tendonish stuff. So you got some serious toughness going on up in the shoulder, if it was a shoulder, again. So what are we going to look at this that really is just spectacular? First of all, this is made of a totally different material than the tendon. Absolutely totally different. Totally dissolved in the flood. If it's separated from the tendon, which I'm going to show you one that did, it would just dissolve. And that's what happened in the ocean, the one I'm going to show you. And all that's left is this. And remember the ball, remember that heavy-duty strap, remember the abrupt transition, and this just erodes away. It's just like nothing. And here it is up above. I think I showed you this in a different shot. The only difference with this picture and this picture is that the ball, the shoulder bone is missing. So what we have here is this over to here is sticking up out of the ocean. Remember the big ball, remember which is this ball here, and that comes out, and the abrupt transition, and this is just nothing but heavy-duty strap. And this erodes, and the ball erodes. And what did we just see in the ocean? I think I might have shown you this, or I definitely will at some point. This is the tendon. And that's all it is the tendon. That's the ball, and the bone would have been right here, and that other ball in the bone, and it erodes and just dissolves in the ocean. And this side was where the muscle went, and that just dissolves. This is the tendon, and it's tough as hell. Now, here's the problem with geology, archaeology, history, because of this. How long do you think it would take a gigantic creature, I mean gigantic, that had a shoulder like that, which I showed you, this could be from a shoulder, because the creatures were gigantic. I don't care what anybody says. They were absolutely enormous. How long do you think it would take that creature to die? I'd say maybe, let's throw caution to the wind, and we'll give them a couple of days. I would say it's going to be within hours. They have red blood just like us. Same blood, no difference. Well, some of them had gigantic red blood cells I showed the other day. Some of them were almost 4 feet across, and those were just the cells in the body. Now think about this now. This thing dies. He's dead. Millions of years in one picture. No, I don't think so. They say, oh, there's another 100,000, another 100,000, another 50,000, another 60,000, another flood, another this, another that. No. That is like a weekend, my friends. Okay, this goes so far beyond extreme coolness, I can't even imagine anything cooler. I found interstitium in my mud fossils, and I knew it was something different than what they were talking about. They didn't realize it was there. And all this relates to is this little layer right here. Nothing else. They knew about interstitium, fascia, they knew all that stuff. They didn't know this was an open fluid-filled highway. I made a paper about this in 2015. I called it a fluid-filled network that fuses together as one giant system. And it was used in fascia-facilitated fossilization. Because that's what I was finding fossils. This is a DNA-tested human lung from, I believe, what they considered, anyway, I'll talk about that later. But this is the coating, the fascia. and it died flat as a pancake. It was in a flood. And MIT says there was a boiling hot event and the oceans literally boiled. It just happened the other day. They admitted it. I've been talking about it for years. Velikovsky said the same thing in 1950. And they forced him to take his book off the bookshelves because it was so well received, and they hated it, the academics. So anyway, they took his book off, and nobody's ever talked about it since because they would be dismissed, which they have been. So I can talk about it because I can't get dismissed. I'm already dismissed. No, I took the blood right out of here and sent it off. You know, not blood, but, well, it's as good as blood. It's just dried blood, literally dried blood. You get dried blood out of there right now, and I've shown this over and over and over. And the rest is the pleura of the lung. And I could see all this stuff in my mud fossils. And I have mud fossils here that not only have the pleura on them. Well, let me show you one right here. Hold on. This one right here, same thing, same event, same flood, flat as a pancake. You see it? Another lung, and the pleura has partially eroded away. You see that? That's the lung. That's the attachment at the top. It still has the spur lock on it, which they all have. This one does too. And the pleura has eroded away, and it's a heavy, dense. This is a big rubber bag. It does this 24 hours a day, or you do not continue to consume oxygen. And in that case, it would not be a good thing. Now, so here's the layer that I found. Now, listen, wait do you see this? This goes so far over the charts, it's just unbelievable. Now, I also realized that certain things could turn into opal, or they could turn into transition metals, depending upon the orientation of the body and how the blood flowed and how big the creature was and all that stuff. And if you were in the right conditions, you could replace the whole thing with transition metals, basically, because they have polarities on them. They will want to bond with things, and they'll work their way around and turn things into colored objects. And depending upon if you're in an area where it's just nothing but heart blood, artery blood specifically, because that's the stuff that moves. Well, let me just show you something. Where do you see this? Don't forget this layer. Nobody knew it exists. By the time they had it in the autopsy room, it was flat as a pancake. They thought it was one very thin sheet. If you read it up, this is from 2018. Meet your interstitium, a newfound organ. This whole thing, and this is the paper they finally put in 2018. I put the paper out in 2015, the exact same thing, that this was a fluid-filled highway network that could combine with the whole body as a giant network. And now I have discovered there's two little points on every bag. So in other words, this is a bag. This is completely covered to protect it from any invasion. Nothing should get through here. Nothing, unless it's allowed. Right? And then at the end of that bag, it attaches to another bag. That's that little thing I'm calling the spur lock. And here's one right on here. You see that little latch? That little latch has two little dots on the end of it. And they all do. And those two little dots transfer this fluid, which is encapsulated in this bag, which is just a completely sealed bag. That's the whole idea of the fascia that surround the organ. Don't let anybody get in here. That's the fascia. That's why it's here. Now, cancer and other invasive diseases, they penetrate the membrane. All right, and every membrane has to be different because there's a couple hundred types of cancers. So every one of them, and they say they're all related to organs or tissue types. So it's the fascia that protects it, I say, is being invaded. And the only reason it can get invaded is it doesn't have the correct chemistry to fight back. Hello.
Hi.
All right, I've been told it's time to wrap it up. I just showed you this layer right here. And this is considered to be a newfound organ, which is that layer. Well, guess what? This is that layer too. Let me get a different shot of it. Right up there, that layer right there. That's the layer of, hold on. All right, I just showed you that layer. Here it is right here. That's the fluid-filled highway. It's emptied out. This has taken in all the transition colors of blood. And this is the layers of tissue. The skin starts here, then you put your fluid-filled highway to protect you. Then you have your membrane. Then you have your muscles and your sarcomeres under here. You see those little those little blocks? I have a blow-up of this. Hold on. You see, that's the fluid-filled highway. It's drained out now. That's the membrane. And it has its own layers. The membranes have their own layers. And of course up there is the skin and so forth. And down here is the muscles. And these are like the blocky muscle sarcomeres. And when they twist, they become easy to see. So I don't know what this creature was, but I can tell you one thing. That is from an area where it was just flush with red blood. However, you see the black in between the red? You see that? They don't want to be, they will not mix. It appears to me they don't mix. The black and red does not mix. And this is some gigantic thing because this is a tree. I don't know. These things were huge. You see this? This is red blood pushing away the black blood. There's something to do with the polarities here. Now watch where we are. Don't forget, red blood pushing away the black blood. Where are we? All the red blood is pushing away the black blood. You see it? It's almost like an abrupt transition. Well, basically it is. So the red blood is pushing away the black blood. And in between the red and the black is like a semi-red. So, where is this? Well, this is right below Typhon's throat, where they cut his throat. This is Typhon in the desert. There's his neck, his head, right from there down. You can come up and look at it. It's right here. All right, and there's the fish. All right, I have to run, so I got to stop. But this is Typhon. He's in the desert. You can come up and see him. He's very easy to see. And there's a giant fish that he was trying to kill. And this was where his throat was cut, according to Apollodorus and all the rest of the ancient sources. That is it right there. And you can see the black is being pushed away from the red everywhere. The red is staying away from the black. They hate each other. It's polarity. It's got to be. You see that, how abrupt that transition is? There's no mix. There is between the red and the black, there's a sort of a different color in spots, which is the red, yellow, black. It's polarity, my friends. There isn't, and this is a gigantic dragon. I'm sorry, that is just a fact. These are the scales on his throat. And again, come up and look at it. I've shown this hundreds of times, and I'm frankly tired of showing it. Okay, I'm going to pretty much get ready to wrap it up, but this is on Mars. These are or they're sarcomeres of muscle, whatever. And the red blood has just dusted off of it. And it is on Mars. There's no erosion whatsoever because there is no water on Mars. But the radiation causes the erosion, basically, which is the dusting off of the red blood that was in here. That's what sarcomeres do. They have red blood in them. Now, this is what the sarcomeres do look like. Remember what that is. Here's what they look like right here. Now, they pull together and they come like this. So here they are relaxed, here they are contracted. And it's because of the red blood. And the red blood has run out and all of these, the gooey parts have just eroded. And this is what they look like, which actually this is a true rendition of it. But a better one would be this one right here, right there. Well, this is in a rock. That's right there. That's the very, very top, the skin. Then you go into a little bit of a subskin, and then you hit the muscle sarcomeres that are. And this is all the blood that has to service those sarcomeres, because they take tons of blood. And that's where the Mars crab comes in. I don't know if I have it shown here, but you got the Mars crab, Mars blueberries, and the Mars Morse code. And then, as I just showed you here, this is nothing more than muscle. That's nothing more than muscle up on Mars. They say this happened over millions of years. No, this happened at the impact point when Mars actually did hit Venus. I mean, Venus actually hit Mars, and it just wiped it out, wiped out the atmosphere and destroyed the whole thing. And you see those sarcomeres I just showed you over in Turkey? They have the same thing. These are muscle sarcomeres on this mountain grove, a mountain here. And the red blood ran out because it's on a downhill slope, and the red blood layers ran out underneath, and this whole thing collapsed. These are muscle sarcomeres. See? And they go straight down, and then there was a layer way down at the bottom. I had pictures of it, but I can't find it anymore. But it was below all this stuff where all the red blood ran out. And then the whole thing just dropped. Look at these. These are people standing here. You see, that's blood right there. And these are the sarcomeres. And it takes a ton of blood to run these things. So the blood ran out, and there's some more blood over here. And just like I just showed you a second ago, those are the sarcomeres. Now think of this. Think if this thing was twisted up like this, and they're growing all their crops up here, and they're having a good time, and their life is good, and the slope is this way, and all that stuff ran down and out. All the blood ran out because it eroded out. This stuff is weak. It erodes out, and all of a sudden, all of these blocks just dropped. And that happened in Turkey. Now, I've been reporting on this for a while. I thought maybe somebody would take an interest, but I haven't had anybody respond. So, and this is right up here, that's the surface of the Earth. And basically, this was the skin. And this is right above the muscle sarcomeres. And there's good vitality in that particular layer. That's why it grows well there. What else can I show you? I showed you this is connective tissue, I'm quite sure, and this is like muscle fibers, I'm pretty sure. This, I feel confident in. The banded iron is a different issue. That, I believe, is just red and black blood pushing each other apart into layers and layers and layers. It looks to me. If I had, well, anyway, that's what it looks like to me. And that, I don't know, must have been a big artery or something coming right in there. And this, whatever that is, I don't know. But I say that is the push to shove of those polarized iron particles, and that's what they call banded iron. And again, it can form in any way, and this is banded iron too. You see, this is one side, and that's the black side, and push to the other side. That would be like laying in here, and you'd be looking down at it. That's the black side, and that's the reddy side. And but this was from an organ. This is an organ. I'm not sure what it is. I got a feeling it's a liver or something. But you see how it's got all those layers in there? And that's what splits it open. I was always wondering why these rocks had layer after layer after layer. For no reason. And it's because the black and the red snap it open in these tendon balls. And I'll show you just real quickly, and then we're going to wrap it up after that. But I think I've made my case very clearly here, I hope. And if I haven't, tell me why. What didn't you see? I showed the tendons. I showed all my muscles and things I have here in my shop. My stuff, a lot of it's been, well, 3 of it's been DNA tested. Here's the sarcomeres in a heart. And asteroid Bennu, they just came back, has the same sarcomeres, and it has the phosphate layers above it. It's from a heart. Bennu is a heart, and they have brought it back to Earth, so that it's here on Earth. There's no reason whatsoever we shouldn't know today if that's a heart or not, which I already know. All you got to do is look at it. It's got the sarcomeres and the 2 phosphate layers. So I think we're just spinning our wheels here, trying to do something that costs a lot of money for just in the interest of funding, as far as I can see. And don't forget, there's the transfer into these, what they call the seashells, which are not. They are the lung alveoli. And that's the surface of the lung. This is amazing she found this piece. Because the surface of the lung is pretty thick, and then it starts right into the alveoli. Of course, she's on the top, and she's right above there, so I guess that's what would fall off first. But to me, I think it was a pretty amazing. Very amazing. And that's this thing right here. And I showed you how we got the layering here. The red on one side, the black on the other. I got interrupted a bunch of times. I don't know if I showed you this yet, but here's NASA. Potential life beneath Martian ice. Well, let me tell you something. They should have paid attention to what was right in their face. These are the Martian Morse codes. And they saw this in 2015 and just dismissed it. That is pinched together skin. That is stretched out skin. That is skin. These are the tendon enthesis balls for the skin. This is pinched skin, stretched skin, just, not, just normal skin. This is the Mars blueberries. They're identical to the Moki marbles. And those are also the interstitium balls with the straps completely eroded. And here is the Mars crab. That's a vein and an artery, And these are the legs of the artery, and they're going into that sarcomere. All those muscle sarcomeres down here, you see them? Same stuff I've been showing you. All that is there. This goes back to 2015, 10 years ago. The amount of money spent is staggering. And I showed you these muscle sarcomeres. They're just eroded. All that dust coming out of them means that it just dried out and came out, because there's no moisture on Mars to speak of on the surface. And here they are, is the identical same sarcomeres in heart attack victims. Same sarcomeres, only these didn't dust off like they did up on Mars. And on Earth they won't, but on Mars they do. You see, that's on Mars too. Oh, continually over millions of years. No, it was when this event happened right here, when Venus impacted Mars and crushed through Mars and wiped it destroyed it and killed all the creatures on Mars, spit all kinds of things into space, combusted the whole thing and turned it into the red planet because it killed all the creatures and burnt them up and boiled them and all that. That had to be a wet planet too. And all of that vaporized and all of those creatures turned into mud. We got basically the same thing. The mud on Earth, is nothing more than eroded body flesh. There's a red bed layer, which is the mud. And then there's gray clay and black cap. That's the Triassic layer. But the red bed is either eroded plants and things and stuff, or it is from the Great Flood that boiled the flesh off these creatures. Literally boiled the flesh off. That's why we're down to the body parts, like the lungs. All right, it's the stuff with the heavy fascia that really was protected well. That's why I call it fascia facilitated fossilization. And the giants were here. I got everything. There's nothing I don't have. I can support every single word I have said with DNA, CAT scans, samples, tests, anatomists, chemistry. I know the whole 9 yards now. There is nothing I don't understand. Zero that I don't understand now. 15 years, and now we need to get somebody that can look at a heart and say, yeah, that's a heart. Wow. Let's look into this instead of... These things are real. And I got people all over the world now reporting to me because nobody will talk to them. So I've got probably, as far as I'm concerned, probably the best sources in the world right now. And I have all the best specimens, there's no question about that. I've got specimens nobody has. And I've got them virtually of everything. You show me something and I can probably show you a specimen. And this is where the transition metals are, and you have to understand these charges. And this is why you got to understand chemistry. You got to understand dipole electron flood theory. That's the key. Nobody understands that either. That's why they don't even know what gravity is. I'm not kidding you. They do not know what gravity is. Isn't that amazing? And dark matter, we can't find a dark matter. Well, dark matter is half of light. Light, everything there is, half is dark matter. The black goes to the center. The white goes around the outside. We never see anything but the white because that's what bounces back. It's inside of everything. These are the two particles, the only two particles make up everything in the universe. Everything. Those two together are electron, or it would be called an electron. And four of those, which is two of these and two of those back to back, is bar magnets, make up a photon. Here it is right here. These are electrons, gluons, and two of them back to back make up a photon. This will stick to something and cause heat. This will bounce because it's got a field completely around it. This has only one field. So this sticks, this bounces. That's light, this is heat. If you can separate the white from the black, which we did in our experiments, you create electricity. The white itself, all by itself, only the white, separated from the black, that's electricity, that's lightning, that's static. All that wants to do is to get to ground, which has all the dark matter. You're standing on something solid, you're standing on dark matter. Earth is primarily dark matter. And the white, all light wants to hit the ground, all electricity, all lightning, all static. And it'll go right through you, right through, explode you to get to the ground. That's how powerful that thing is. But you got to get it away from the black. If you can do that, you're golden. And we did that. And nobody seems to have any interest. This has been 10 years. And our national laboratories don't care at all. Redshift's crazy. Like the whole universe is pulling away in every direction. So we're the center of the universe, and it just pulls the light away, making it turn red by the time it hits us. No. It's slowing down. And it's slowing down from every direction. That's all. Simple as that. And they just can't accept that because Einstein says it never slows down. It slows down and it speeds up. Light has no speed whatsoever. Light is only faster sound. Sound is light, but it's just going very, very slow. That's all. You see this? Sound is way down here. Very long waves. Ooh. Then it gets, and then it goes faster and faster and faster, which is the spin. Right down here, it's just spinning slow enough to be audible. Up here, it's spinning fast enough to vibrate water in a microwave. That's what makes a microwave cook. Up here, infrared is warm enough to warm your body. Heat, heat. Up here is visible. You can see all these different colors, and that's all there is that we can see. Then ultraviolet, that's a little dangerous. X-rays, obviously dangerous. And then you hit gamma rays. Why? What do we have between ultraviolet and gamma and X-rays? We have what's called the ultraviolet catastrophe. That means the ultraviolet gets spinning so fast, the energy goes way up like this, and then all of a sudden it goes right down to zero. But nobody can account for that. I know exactly why. It's because it spins so fast that at a certain spin rate, all of the electrons are gone, so there's no more energy, basically. There's just that mass, which is X-rays and gamma rays, and that is the part that kills you, because it's just the black part at this point. The white has been thrown off. It's just spinning way too fast. And the white part goes, and the black just continues on and creates X-rays, which are real fast particles, and then gamma rays, which are just off the chart fast particles. And those are the ones that damage you. But don't forget that, look it up. Ultraviolet catastrophe. At a certain rate, it goes up, 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 and which is energy. And then it goes blip, right down to 0. All right, so I'm going to leave it at this. I've been watching TV a lot lately. They're talking about the cost of college and forget about going to college, go to trade school. I agree with that 100%. Come to Mudfossil University. I can teach you virtually everything, because what you're going to hear is just not true. This potential for life under Mars ice, they're talking about things that have already been solved. Bennu asteroid is a heart. No question whatsoever about it. 100% case closed on that. My stuff is all DNA tested, and I got CAT scans, I got specimens. The giant creatures were here, the dragon in the desert, everything is here. They will not teach you this. So they, as far as I'm concerned, should know this, because I've been pushing it on every university. I went to, I didn't go to Yale. I sent all my information to Yale, and they just dismissed it. Of course, Harvard, every one of them, Johns Hopkins. And I actually did go to Johns Hopkins for genomics. And my professor, within 8 minutes of me sending him all my stuff, which was CAT scans, DNA tests, pictures of specimens, anatomist autopsy reports, chemistry, everything. 8 minutes, I got a thing saying I must be out of my mind. And that, obviously, that did not set well with me. So I'm going to tell you right now, college is not necessary for the, like they say, liberal arts or whatever they call it. If you want to go learn about plays and Shakespeare and all that, that's good. Have a nice time. If you want to learn about science, come to Mudfossil University. You want to learn history. You want to learn archaeology. You want to learn geology. You want to learn about space, astrophysics. You want to learn physics in general. You want to learn about the atomic, everything to do with this new standard model. The standard model's wrong. This is the new proton, is this. Standard model is just totally wrong. And then I saw Mikio Kaku talking about there is no electron, there is no this, where's the beef? Here's the beef, and now I want to talk to him. Just listen to this. Listen to what he has to say. He's talking about string theory. There's no electron.
There's no electron. There's no proton. There's no neutron. Matter as we know it is not there. Therefore, it cannot describe the universe. String theory is the only theory that combines Einstein's theory of gravity with a theory of particles.
First of all, Einstein totally wrong, 100% wrong about virtually everything he said. Speed of light is totally variable. Light is a particle. It has a wave around it because it's got a big field surrounding it. Forget about it. String theory is not correct, but it's not completely totally wrong. Now he's saying this is the only thing that works. Now listen to what else he has to say. All right, so he's saying it's the only thing that combines everything. Combine nothing. Start from scratch, because they don't know what the standard model is, just wrong. So forget about that. All right, what I show, I think Mikio Kaku should talk to me. He's saying string theory and particles fulfills the requirements, only there is nothing, nobody can show it. Listen.
The main criticism of string theory, which has to be taken seriously, is, well, where's the beef?
Where's the beef?
Where are these particles that are predicted by string theory?
All right, string theory, I'm not saying it's correct or it's wrong, but I can show you the particles that make up the proton, which I have over and over and over, and in experiments, not just theoretical. I'll show you the beef. All right, if I understand string theory correctly, and I'm not sure if I do, but they claim that the nucleus holds onto these little tiny particles with strings, basically. Some strings are longer than others, and so forth. Well, to a degree, that's correct. If you consider the strings to be magnetic energy, all right, and I will show you there will be different strengths of these magnetic fields, which you could call them different longer strings. And there is a core, and these are the particles. Now, when you get below the nucleus of an atom, you're into into tinier particles, which in this case is photons. You can break these photons down, as we did, into their constituent particles, which is the muon and the electron neutrino. And here's exactly what we did. Putting it through the Venturi, the black stayed behind, the white went through and recombined with the black. So here's the light accelerating, the black stays behind, which is the muon neutrino. So we have a sterile muon. And here we have electron showers coming through the white showers. It recombines here. That says that's fission, that's fusion, and the time of entanglement between here and here is a certain time and a certain distance. But that relates only to red. Green is going to be way out here. It's going to re-engage way out here. It'll separate here, yes, but it'll come back way out here much further because it's much more powerful. So entanglement is related to the speed of the spin, which is the color. The slow spin way out here, it's spinning, but it's slow, and it looks like a wave if you look at it from the side. I agree, but it's slow, and it recombines pretty quick. Now the green is going rocket ship fast, but it's closer. It's spinning faster. That means it's more push. The distance between the waves, or the distance between the spins, basically, is how much push there is. That's energy, that's voltage. The wider the push, the fields are further separated. This is very, very simple if you understand dipole fluid theory. The closer they are, the fields are very close to each other and it's pushing like hell. And when you get down to blue, they're just right on top of each other, beep, and it's gone. And it's powerful and it's energetic. That's why you create more and more and more energy. High energy and high frequency goes that way. Shorter wavelengths, shorter. Longer wavelengths, low energy, low frequency, all the way down to sound, vibration. That's all it is. Tesla, with his vibration statement about, energy, I forget what he said, but he relates everything to vibration, and that's true. It's field against field. It's push to shove, push to shove. I hope that made sense. Okay, I'm just going to let him finish up and then we're done. He's saying string theory predicts everything. Basically, and if it's what I'm thinking it is, it's holding on to those particles basically like I show right here. This, to me, would be the first length of the string is to the blue, and that's tight. That is held tight. If you pull that away, it's gone. It takes off and it'll never come back because it takes so much energy to pull it away. The green is that long. All right, that's the length of the string. The red string is way out here. The green will pull and usually go and never come back. The red will pull and bounce around out here because it's not held all that tight. It just sort of flexes in and out because it's still being held, but it's not enough push away that it takes off and doesn't come back. And that also, you see that in Fermilab's portrayal of what happens when they crash things. They see all the blue gone, white gone, green gone, red just sort of hangs around. Okay, my friends, so I'm going to tell you, forget about school as far as any of the stuff they're teaching you now. It's just not correct. Literally nothing. I mean, almost nothing whatsoever is correct. Almost nothing. Geology is totally ridiculous. Everything's made from mud fossils, and that changes everything. This means change, a triangle. Changes chemistry because now I understand dipole electron fluid theory, biology, physics. You just see physics is totally wrong. History, mythology, religion, anthropology, archaeology, human development, evolution. There was giants, there was dragons. The myths seem to be quite true to me. Physics, the light, is made nothing but half and half of dark and white matter. And now that solves the dark matter and it solves gravity. Gravity is nothing more than the dark pulling the white to it. And the white has no mass whatsoever. You fill your car up with electricity, which is the battery juice. It gains no energy, no weight whatsoever, none, zero. There's no weight to that particle, none, zero. That has all the weight. And the two of them together make up the light. I just showed you what a photon looks like. Periodic table's all wrong. It's got to be changed. Enzymes and the complexity of click chemistry and how the enzymes work to make life work and how proteins and catalysts work in the body and bacteria. All of that stuff is wrong, and it goes on and on and on and on and on from there. It just never ends. And space is not a vacuum. And here's again, Don Lincoln Fermi Lab. Empty space isn't empty. It's full of subatomic particles that wink on and off. And it says it has a measurable impact on our universe. Yes, it slows light down. Why can't they accept the things that they can? You have to be able to understand this. These are people that we've given billions and billions for trillions of dollars to. This is 10 years ago. And I showed all my stuff to Don Lincoln. I showed him exactly the same particles that he was trying. Right here. These are the particles. They do exactly what he says. And we found them in our light experiments right here. There they are. There's his particles. There's ours. No difference whatsoever. And we can focus ours and make Higgs fields and do all kinds of stuff. And we can see those particles manifest and crash into the Ventura and explode. And we can see them in green and red at the same time. And you see how far out the green goes? The red just gets pushed out of the way. It's cheap. It's got no real power to speak of. The green is very powerful. It reconcusses way out here. That's why I say it's the spin rate. But that's the green particle. Green is a little harder to photograph than the red. Although Rod got the green fabulously. Anyway, I showed you so much stuff. I'm done for today. And I'm sorry I've taken up so much of your time. But do not waste your money on college. It's just a waste of your money if you're taking chemistry or this or that. This is wrong about everything. I mean, chemistry, I work below the atom, okay? So chemistry works above the atom, basically. I'm in the subatomic range. That's where I primarily, and isotopes, and how particles form. And it's called nucleosynthesis. And what does nucleosynthesis mean? Nucleuses, which means the core of an atom. Synthesis means rebuild it, change it, synthesize it, make it into something else. And that's what happens when you put enzymes, which come from bacteria, and they're extremely elegant chemistry sets. They break down molecules, and then they reform them into new stuff. It's almost instantaneously. They run millions of times faster in the chemical complexes than they would if they were left to do it on their own. It would eventually happen, but it would take years. In their quarter of a second it's done, and then because it's click chemistry, that particle isn't used up, that enzyme. It goes to another one, goes click, 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 and it changes everybody. As soon as it hits it, done. Click, done, click, 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 click. It's a magnetic impulse, basically, is what enzymes do. They're like magnetic impulses. Bam, 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 bam. They don't get used up. They don't get consumed. And I guess when they're done and there's just no more need for them, they just dissolve. But they come from ribosomes. Ribosomes come from ribosomes create the enzymes, but the ribosomes come from bacteria. So the bacteria is the source of all, basically, as far as I'm concerned, the chemistry in your body. You don't have the enzymes, the bacteria, the chemistry will not happen. It just will not happen. And this chemistry has to be there in this layer that I showed you, this specific layer right there, to keep the invasion at bay, keep them out. If it gets poked through there, which it will eventually, you get a cut, which I just got a whole batch of them in my face. It'll go in here and it'll fester a little bit because your fluids will come and attack the damn thing. And you got so much of this fluid, you should never, ever, ever be attacked beyond repair because you got tons of fluid. However, you don't have the right chemistry in that fluid. I don't care what happens. You could have tons of fluid. We're not going to help you. This thing's going to come through and launch in there and just live inside of you and grow a tumor or whatever. They become obstructive. They do all kinds of things. They create all kinds of after effects, poop and all kinds of things in there. They're living inside of you. And something's got to clean up after it. And maybe you don't have the stuff to clean it up. But somehow it got through that membrane. That's my point. Now, again, I'm sorry that it took so long, but have a nice day. I love you.